Welcome to my class. I want to, in today's lesson, look at revision on properties of determinants and the transpose. So we'll be looking at very interesting examples along the way. Now, so let's just begin with examples straight away. The first example that I want us to look at is this. Find a condition. Find a condition. Just a minute, let me just write properly here. Find a condition on the numbers ABC so that the following system is consistent. Find a condition on the numbers ABC so that the following system is consistent. And then the question says that when that condition is satisfied, when that condition is satisfied, find all the solutions. Find all the solutions in terms of ABC. So the question is, find a condition on the numbers ABC so that the following system is consistent. When that condition is satisfied, find all the solutions in terms of ABC. Now the system that I'm referring to is x plus 2y minus z is A, and then 2y minus 2z is B, and x minus y plus 2z is C. Now, so you know what a consistent solution system is. This is a system that has a solution. And we said last time that a system that has no solution is referred to as inconsistent. So what the question is asking is, the question wants us to find what should ABC be, what would be the condition such that this system would have a solution. So the question is, what should happen? What should happen to ABC so that, or to the system, so that the system would have a solution? So that is what the question is asking us to do. So that's what we want to do. For us to answer this question, the only thing we need to do is reduce this system to echelon form and see what the last line of the echelon form would tell us. So let me just create a space. Let me create some space for this. Now, so look at the solution to that question. Reducing to echelon form. So we just want to reduce that system to echelon form. And the system was x plus 2y minus z is A, and 2y minus 2z is B, and then x minus y plus 2z is C. Now, so I want to reduce this system to echelon form. So I want this to be the only non-zero element in column 1. So you can see that this is x. I was 0 here, 0x. So I want also this one to be 0. So what do I do? What I need to do is that I want to subtract the first equation from the third equation to get my new third equation. So what we then get is that the first equation remains where it is. The second equation remains where it is. And then I'm subtracting the first from the third equation. So x minus x will be 0. Negative y minus 2y will be negative 3y. And then 2z minus z will be 3z. And then c minus a will be c minus a. Now, so I also want this to be 1. I want this one to be 1y, and then use it to create a 0 in this position. I want this one to be 1y, although I can work with it the way it is. It's 2y, but to make my work easier, let me first of all make it 1. So what do I get? The first equation remains where it is. The second equation, I'm dividing this equation by 2. So I would have y minus z is b divided by 2. And the third equation remains the way it is. And then what I want now is to use this y to create a 0 in this position. So what you notice is that I'll need to multiply this second equation by 3 and then add the result to equation 3. So the first equation remains where it is. The second equation remains the way it is. And then I multiply this second equation by 3 and add the result to the third equation. So y times 3, you get 3y. Add to this, you get 0. Negative z times 3 will be negative 3z. Added to this will be 0. What about this? So what I have on the left side is 0 equals, the right side I have c minus a plus 3b out of 2. So when I multiply this one by 3 and add the result to this, that's what I get. So the question is, we already have this system now in echelon form. The question is, what is the condition on the numbers ABC such that the system here would have a solution? Now when we check on our echelon form here, echelon form of that system, you notice that on the left side we have a 0 and the right side we have c minus a plus 3b out of 2. Now what we said in our earlier video is that if this right hand side will also be 0, so that we have 0 equals to 0, and then this system would have a solution. But if the right hand side would be something greater than 0, or let me just say something different from 0, non-zero, if it will be non-zero, so that we have 0 equals to a non-zero element here, then this system would have no solution. It would be inconsistent. So we want the system to be consistent. That means the right side must also be 0. So the condition is, the condition for consistency, for this system to be consistent, to be consistent is that the right side C minus A plus 3B out of 2 should be 0. Or one would say that C should be the same as A minus 3B out of 2. If I take this to the other side of the equal sign. So if I take this to the other side of the equal sign, then you notice that I would have C equals to A minus 3B out of 2. So this is the condition that should be met by ABC so that the system that is given to us is consistent. So it's either this or this. So what you just realize is that the right side must also be equal to 0 since the left side is 0. Since the left side is 0, the right side must also be 0 so that the system has a solution. Now, so the question proceeded and said that if that condition is met, find all the solutions to the system. So supposing the condition is met, and now we have the condition that this is 0. So what will be now the solution to the system? Okay, let me just get more space so that we do the last part of the question. I'll continue from this part. So let me just copy it here. So what we then have, if that condition is met, then what we would have would be x plus 2y minus z is A, and y minus z is B out of 2, and that is 0 is 0. So now we solve this system from the bottom going up. We solve it. This is how we solve it. So we assume that 0 equals to 0 is not there because that was the condition we wanted to have. So let me just remove it so that we are left with what we can now solve. Now, so you notice here that we have the leading elements in equation 1, the leading element there is x, and in equation 2, the leading element here is y. So then it means that z is a free variable. So we let z be t, and then solve this system going up. So if z is t, what will be y? Then y becomes b out of 2 plus z, but z is t. What about x in the first equation? In the first equation, x is a. So if z was to cross the equal sign, it would be plus z, but z is t. And if 2y were to cross the equal sign, it would be negative 2y. But what is y? Y is b out of 2 plus t. So this gives us, let's just open the brackets and collect like terms. I can see a here. If negative 2 were to be multiplied inside here, remember this t, you would remember it. So let me just open this bracket. If negative 2 were to open here, multiply here, I would have negative b. And this is t minus 2t, which would be negative t. And so what is the solution therefore to the system? The solution to the system is x, y, z, which equals to x is a minus b minus t, y is b out of 2, plus T and Z is T. So this will now be the solution to the system. This will be the solution to the system. The question said that if the condition was to be met, what would be the solution? So, and we say this will be our solution. Now, that was a very good example, and it has covered a lot. Let's look at another example, and just another example. But before that example, I want us to look at some theorem that I state here without proof. So I'll not prove this theorem. The proof exists. You can look for the proof in the textbooks. So the question is, the theorem is, let A and B be matrices. Let A and B be matrices of the same size. So you know what the size of a matrix is. Now the question is, let K denote a scalar. Let K denote a scalar. Then part A of the theorem says that the transpose of T transpose, the transpose of A transpose will be A. And that, in fact, what this means, just before I continue, what this one means, if I was to give an example, you know, if A is 2, 1, 0, 1, 3, 4, then what is the transpose of A? What's the transpose of A? The transpose of A, we say, we write the rows as the column. So the first row here becomes the first column, and the second row here becomes the second column. So this is the transpose of A. What about the transpose of A transpose? The transpose of A transpose. So this is A transpose. So the transpose of this, the first row becomes the first column. The second row becomes the second column. The third row becomes the third column. So you notice that the transpose of A transpose is A. That is what this statement says, that the transpose of A transpose will be A. So let's look at the other part of this theorem. The other part of this theorem is that the transpose of Ka will be the same as K times A transpose. And then lastly is that the transpose of the sum of A and B, the transpose of the sum of A and B would be A transpose plus B transpose. So this is a very important theorem, and we'll be using it in some of our examples that will proceed. So let's remember this theorem. And very importantly, that the transpose of A transpose will be A, and that if I were to take a constant, K is a constant here. K times A, the transpose of that will be K times A transpose. And the transpose of the sum of two matrices will be the same as the transpose of the first matrix plus the transpose of the second matrix. Now I want us to look at another theorem that is also very important, and again I'm stating it here without proof. The proof exists. You can find it in the books. I'm only interested in the application of these theorems. So the theorem says that if A is an invertible matrix, that is, if A is a matrix whose inverse exists, that's what it means, then the inverse of A inverse exists. That is why I say so is that. And therefore, the inverse of A inverse would be A. The inverse of A inverse would be A. So what I'm saying is that if the inverse of A exists, then the inverse of A inverse also exists. And therefore, the inverse of A inverse is just A. Let me just show you an example. If suppose A is the matrix 2, 1, 1, 0. What is A inverse? First of all, to find A inverse, we must find the determinant of A. And the determinant of A is 0 minus 1, which is negative 1. So that means that A inverse is 1 over the determinant multiplied by the adjoint of this matrix. So we just reverse this diagonal and change the signs for this other diagonal. Reverse this diagonal and change the signs. So the A inverse will just be, when I multiply this one inside, I'd have 0, 1, 1, negative 2. This is A inverse. So what about the inverse of this? What about the inverse of A inverse? So again, I would find the determinant of A inverse. I would find the determinant of A inverse, and that would be 0 minus 1, which is negative 1. 0 minus 1, which would be negative 1. So what about the inverse? Just a minute. What about the inverse of A inverse? So that would be 1 over this determinant. 1 over this determinant times the adjoint here. So we reverse this to be negative 2, 0. And change the sign there. Negative 1, negative 1. So when I multiply through with this negative 1, I would have 2, 1, 1. This was 0. So again 0 here. So what you realize is that the inverse of A inverse is A. The inverse of A inverse is A. That is what these theorems say. So I want us to use the two theorems in the following example. So what does the example say? Example says, find A if the transpose of A plus 2i, where I is the identity matrix, the inverse of this gives you 4, 1, 1, 0. That find A. What is A if A transpose plus 2i, the inverse of that gives you 4, 1, 1, 0. So solution, for me to do this question, I would use the theorem that has just, the last theorem there, which says that the inverse of A inverse is A. That is the theorem I will begin with. So using that theorem, what I need to do is find inverse on both sides. Finding inverse on both sides. What we would have is A transpose plus 2i inverse. Then the inverse of that will be the same as 4, 1, 1, 0 inverse. But I know what the left side is. What the left side is that the inverse of this inverse would just be A transpose plus 2i. That's what we learned. That's what we learned. We learned and said that the theorem says that the inverse of A inverse is A. That means the inverse of this, supposing this is A, then it will just be A. So the inverse of this inverse is just that. That's what that theorem says. So what we need to do is to find the inverse on the right side. But the inverse on the right side, first of all, we must get the determinant on the right side. So the determinant of 4, 1, 1, 0. The determinant of this is 0 minus 1, which is negative 1. So it means that the inverse of 4, 1, 1, 0 is 1 over the determinant times the adjoint of this 4, 1, 1, 0. So we reverse this diagonal and change the signs there, negative 1, negative 1. So that this inverse therefore is 0, 1. If I were to multiply through by the negative 1, and this would be 1, and this would be negative 4. So that what I now have is that A transpose plus 2i, but what is I? I is 1, 0, 0, 1, gives me 0, 1, 1, negative 4. So what is A transpose? I take this on the other side of the equal sign. So it will be this minus this. This is 2, 2 here, and 0 elsewhere, if I was to multiply through by 2. So if I take it the other side, it becomes negative. So what I have is 0, 1, 1, negative 4, minus 2, 0, 0, 2. And what does this subtraction give us? It gives us negative 2, 1, that is negative 2, 1, and this will be 1, and this will be negative 6. So this is A transpose. What about A? So I take the transpose on both sides, because we learned that the transpose of A transpose will be A. So I take the transpose on both sides. Let me just write it here. Taking the transpose on both sides, taking transpose on both sides, what do we get? Here, the transpose of this would be A, and the transpose of this would be negative 2, 1, and this would be 1, negative 6. So we've just found A, and that's what the question wanted us to find. The question wanted us to find A, and this is what we have as our A. So the question, look at how the question was, that find A if the transpose, the inverse of the transpose of A plus 2i is this. So we used our two theorems above. The first theorem we used is this, that the inverse, we take the inverse on both sides. So the inverse of this will be that, and then we find the inverse of this. So the inverse of this, we found it to be this. And then we come back to the question from this point. We come back to the question from this point here. A transpose plus 2i, but I is the identity element. These are 2 by 2 matrix. That means we have I is the identity element for a 2 by 2 matrix. And then make the A transpose the subject of the formula, and from there we take the transpose on both sides to have our A. That's how we do this question. And let's look at another example. The example is find A when 2A, the inverse of that, gives you 1, 2, 0, negative 1. So the question is, what is A? So again, I would use the theorem that we just learned, the last theorem. Get inverse on both sides, get inverses on both sides. So if I do that, I would have 2A is 1, 2, 0, negative 1 inverse. Because you know that the inverse of this, the inverse of 2, the inverse of this, the inverse of this would be 2A. So we only need to find the inverse on the right side. The first thing we do is to find the determinant of the one on the right side. So this determinant is negative 1 minus 0, which is negative 1. So that the inverse there the inverse of that will be 1 over determinant, which is just 1. 1 over negative 1 will just be negative 1, times the adjoint of this. So let me reverse this leading diagonal, the elements there, and then change the signs in this other diagonal. So that if I were to open the brackets, I would have 1, 2, 0, negative 1 as the inverse of this matrix. Now, so the question was 2A is the same as, so when you come back here, 2A is the inverse of this, but the inverse of this we found it to be 1, 2, 0, negative 1. So that means that A, therefore, dividing both sides by 2 would give us a half, 1, 0, and negative a half. So that is our A. That is our A. Now, so let me give you some questions for you to try before we proceed with other examples. Let me give you some exercise, just for you to do the same way I've been doing. You use the same concept to do the following questions, and the question is find A in each of the following. Find A in each of the following. I'll give you the answer so that you do yours and compare your answer with mine. I have 7A transpose is equal to 2, negative 3, 1, negative 1 inverse. So find A there. And what is my answer? My answer is that A is the same as negative 1 out of 7, negative 1 out of 7, 3 out of 7, and 2 out of 7. So just do this question and see if you can get the same answer. Now, as we always do, if you find that the answer, you're not getting the answer, you can always write in the comment section that if you got a different answer, maybe I can advise you on what to do. And again, if you have any comment that you want to make, you can still make in the comment section. The other question is 3a minus 2i. The inverse of this is the same as 3, 5 and 0, 2. So find a. And what is my answer to this question? My answer is that a is the same as 7 out of 9, negative 5 out of 18, 0, 5 out of 6. This is 5 out of 6. That's what I find a to be. Let me just write this one properly. 5 out of 6. Okay, that is the exercise that I want you to try. So let us continue with another theorem that will be very important to us. So let me look at this other theorem. Again, I state it without proof. The theorem is let A be a square matrix. Let A be a square matrix. You know that a square matrix has the number of rows and number of columns equal. Now, so if A is a square matrix, then the first thing is that if I was to interchange the rows, if two distinct rows or columns are interchanged, then the determinant of the resulting matrix, then the determinant of the resulting matrix will be that of A times negative 1. So it will be negative determinant of A. Let me just show an example before we proceed. Suppose A is 2, 3, 1, 4. What is the determinant of A? The determinant of A would be 8 minus 3, which is 5. 8 minus 3, which is 5. Let's try to interchange. Let's try to interchange the row. Here I have 1, 4, 2, 3. And let's see what the determinant of B will be. The determinant of B will be 3 minus 8, which will be negative 5. So this is what this theorem says. That if I were to take a matrix, any square matrix, and interchange the rows, any two rows, then the determinant of the new matrix would be the determinant of the old matrix times negative 1. And you've seen in this example. Okay, let me again continue the theorem. There are other statements of this theorem. The other statement is that if a row is multiplied by a constant, if a row of this matrix or a column of A is multiplied by a scalar, let's call it beta. If a row of this matrix is multiplied, or a column of this matrix is multiplied by a scalar beta, and then the resulting matrix, and then the determinant of the resulting matrix will be the determinant of the old matrix multiplied by that scalar b. So if you have a matrix and then you just multiply that matrix by constant, then what you expect is that the new determinant will be the older determinant times that constant. E.g., let me take A to be 2, 1, 0, 3. And then the determinant of A, as you can see, is 6. Let me now multiply A by -1. I want to multiply just a row. I want to multiply the first row or the first column. Let me multiply the first row by -1, so that I have -2, -1, 0, 3. I've just multiplied the first row only, not the entire matrix. That's why I said if a row or a column of A is multiplied by a scalar, so my scalar here is -1. So what will be the determinant of B? The determinant of B will be -6. So what you've noticed is that the determinant of B is -1 times the determinant of A, because we multiplied matrix A by -1 to get matrix B. So that is what that theorem says. And part C of this theorem, I'm still using a square matrix A. I want to look at part C of this theorem, and then after stating all those parts, we look at examples. Part C says if two distinct rows or columns of A are identical, then matrix A would have a determinant equal to 0. Let me just show an example. Supposing I have A which is 2, 1, 2, 1, so that the rows, first row and second row is equal. What will be det A? The determinant of A will be 2 minus 2, which is 0. So that's what I'm saying. Whether it's a 3 by 3 matrix, check and see if we have any two rows which are identical. For instance, if I have this matrix 1, 0, 2, 3, 4, 7, 1, 0, 2, and I'm asked to find the determinant of this matrix, without wasting time, I would say that the determinant of this matrix is 0, because I can see that row 1 is identical to row 3. So if that happens, then the determinant is 0. I don't need to calculate it. And if you were to calculate, you would still get it to be 0. Okay, what about part D of this theorem? Just create some space. Part D says that if this matrix has a row of 0 or a column of 0, then the determinant will be 0. If matrix A has a row or a column of 0, entirely 0, then the determinant of this A will be 0. What I mean is this: supposing I have A which equals to 2, 7, and there's a row that is completely made of zeros, then the determinant of A will just be 0. You can see this will be 0 minus 0. And so what this means, it doesn't matter the size of the matrix. Even if I were to take matrix B, which is 7, 9, 14, 3, 8, 4, and 0, 0, 0, and I'm asked to find the determinant of this matrix, I don't need to waste a lot of time. I've already noted that the last row is entirely of zeros, and that means this matrix, the determinant will be 0. The determinant of this matrix B will be 0, because I just look at the row there. I've seen that there's a row that is made of zeros. Then the last part of this theorem, part E, says that if a multiple of a row is added to a different row, or if a multiple of a column is added to another column, then the determinant of the resulting matrix would be the same as the one of the original matrix. So if a multiple of a row is added to another row, or if a multiple of a column is added to another column, then the determinant of the resulting matrix, is just that of the original matrix. It's the same as det A. It's just the same as that of the original matrix. Let me erase this part and show you an example, an illustration for this part E. So what I mean by this part E is that supposing A is matrix 2, 1, and this is 1, 4, and I want to take a multiple of this row and add to that. Let me multiply this by 3, no, multiply by 2 and then add to that. So this one by 2 is 2, add to that, I have 4. This one by 2 is 8, add to that is 9, and let this one just remain where it is. So this is A is 2, 1, 1, 4, and what I've done is that I've taken row 2 multiplied by 2 and then added the result to row 1. So this one by 2 is 2, added to that I have 4, and this one by 2 is 8, added to that I have 9. Now let me now find the determinant of these two matrices and see if they are equal. The determinant of A is 8 minus 1, which is 7. 8 minus 1. What about the determinant of B? The determinant of B is 16 minus 9. which is 7. 16 minus 9, which is 7. So that means multiplying a row by a constant, then adding it to another row, it does not change the determinant. That the same thing applies to the column. If I was to multiply a column by a constant, then add it to another column, that will not change the determinant of this matrix. Okay, let's look at examples. The example that I want us to look at. And this is a very important example. It says, let the determinant of ABC, P, Q, R, X, Y, Z be 4. Let the determinant of ABC, P, Q, R, X, Y, Z be 4. Find the determinant of A if A is the same as A plus X, B plus Y, C plus Z, 2X, 2Y, 2Z, negative 3P, negative 3Q, negative 3R. So find this determinant, and we are told that the determinant of this matrix here is 4. So we want to use this determinant, which is 4, to get the determinant of this other matrix. So how do we proceed from here? For us to tackle this question, we have to use the theorem that we just looked at. We know that if we add a row to another row, or a multiple of another row to another row, the determinant will just be the same. That if we multiply a matrix by a row of a matrix by a constant, then the new matrix, the determinant of that new matrix, will be the original determinant times that constant. So what you realize is that in this matrix, I have this row. I had a row of X, Y, Z here. This row has been multiplied by 2. I had a row of P, Q, R. It has been multiplied by negative 3. So let me just factor out those constants. Factor out 2 and negative 3 from row 2 and 3 to get so what do we get when we factor out? When you factor out, you find that the determinant of A would be, I factored 2 and negative 3 out. So what I'm left with is A plus X, B plus Y, estimate, B plus Y, C plus Z, this is X, Y, Z, and this one is P, Q, R. Now, so we've seen that adding a row to another row or subtracting a row from a row does not have impact on the determinant. So the determinant remains the same. So this will be the same as negative 6 into, I want to subtract row 2 from row 1. I want to subtract row 2 from row 1. I would have A, B, C, X, Y, Z, P, Q, R. That's what I would have. Then I want to use this is what I want to use. So I'm looking at this, then looking at what I have. I notice that I need to interchange row 2 and row 3. I need to interchange row 2 and row 3. So interchange row 2 and row 3. And so when we interchange, what that theorem told us is that the new matrix, the determinant of the new matrix will be the original determinant times -1. So that means what I have is -6. Now multiplied by -1 because I'm interchanging the rows. I would have A, B, C, P, Q, R, and X, Y, Z. But I know what this one is. I know what this one is. This is the determinant of ABC, PQR, XYZ, and which is given to us to be 6. So that means the answer therefore is this positive 6. No, this one is given to us as 4. So the answer is this positive 6 times that 4, which is 24. So that is the determinant. That's the determinant of this matrix A. The determinant of this matrix A is 24. And what we used is just the theorem that is above. The theorem above is saying that if you interchange rows, then the new determinant will be the old determinant times -1, and that one we've applied it here. And here we've noted that if you take a matrix, a row of a matrix, and multiply it by a constant, the new determinant will be the original determinant times that constant. So that's what we did. We noted that this row had been multiplied by 2, and this row had been multiplied by -3. So we just factored those two out and proceeded. Let's look at another example. So the example is find the value of R. Find the value of R for which the determinant of A, for which the determinant of A is 0 if A is 1 R, 1 R, and R1. So the question is, what will be the value of R so that the determinant of this matrix will be 0? Solution, let's just proceed and find the determinant of this matrix. So the determinant of this matrix, 1 R, R1 R, and R1. So last time we said that for us to get determinant easily, we introduce zeros. So when we introduce zeros, it becomes easy for us to determine determinant along either a row or a column. I want to create a 0 in this position and a 0 in this position, so that this one is the only non-zero element in column 1. I want to create a 0 here. So for me to create a 0 here, what I want is, I want row 2 minus R row 1 and row 3 minus R row 1. So if that happens, then what I would have is 1 let me just do this. Let me just space them a bit. R. So R times this one, subtract from this, I would have a 0. R times this, R, subtract from this, I would have 1 minus R square. And R times this is R square, subtract from this, I would have R minus R square. And then what about this? This will be R minus R, which is 0. And this is R minus R square. And this is 1 minus R square. So this is what I have. Now, I can now find the determinant of this matrix. Along this column, it will be this one times the matrix that is left when you delete the row of 1 and the column of 1. When you delete the row of 1 and the column of 1, what you have is 1 minus R square. R minus R square. R minus R square. And this is 1 minus R square. That's what we wanted. We wanted to get this determinant and then equate to 0. Now you can get this determinant by just multiplying these values along this diagonal and then minus these values along this diagonal. Equate to 0 and factorize this, what you get. Alternatively, you can realize that this can be factored, and that is 1 minus R multiplied by 1 plus R, and this other one, and R is common, R goes there, 1 minus R. What about here? R is common, so we can factor it out, 1 minus R. And what about this? This can be factored, these are difference of squares, 1 minus R, 1 plus R. The difference of squares, just like this. Now, so what you notice here is that along this column, 1 minus I is common, so we can factor it out. 1 minus I is common in this column, so I factor it out. And when I factor it out, just a minute, just before that, and along this other diagonal, you realize that also 1 minus R is common. I have 1 minus R, I have 1 minus R. So I can also factor it out. So let me factor out 1 minus R in this column. What will I have? 1 plus R here and R here. So 1 minus R will go here, 1 plus R, and it will go here, R. What about 1 minus R here? It will go here, R, and go here, 1 plus R. So this is what I now get. Let me get some space here so that I can proceed from here. I just want to create some space here. I will solve this one. I'm done with it. So what I have is this. What I have is this. What I have is 1 minus R multiplied by 1 minus R. And what is this determinant? What is this determinant? This determinant is 1. Let me just change the shape of this bracket so that I do not confuse myself with 1 plus R, 1 plus R minus R square. So what is this? 1 minus R, 1 minus R, and inside this bracket what I have is 1, if I multiply this will be 1, this will be R, and this will be another R, so that is 2R, and this will be R square minus R square. So what do I have? Is 1 minus r, 1 minus r, then 1 plus 2r, because this will give us 0. So the question is, what is r if this is now the determinant? So what will be r if this determinant is 0? That means equate this to 0. Equate this to 0. So 1 minus r, 1 minus r, 1 plus 2r is 0. So what is r? If I use this first bracket, I'll find that r will be 1. Even this other bracket will give me, if I equate to 0, r will be 1. What about this other bracket equate to 0? You will find that r will be negative half. R will be negative half. So what this means is that for the given matrix there to have a determinant of 0, then r is supposed to be either 1 or negative 1. So that is how I do that question. Okay, let me look at another question here, another example. So today we're just looking at several examples on properties of determinants and transpose. So let me look at this example. Example says is that if x1, x2, and x3 are given, if they are given, show that the determinant of 2, 2, 2, x1, x2, x3, x1 square, x2 square, x3 square would be the same as 2 multiplied by x3 minus x2, x3 multiplied by x1, and x2 multiplied by x1. So the question is, show that this determinant is the same as that. Solution. So I noted that 2 is common here in this row, so I factor it out. Factor 2 out. We'll have 1, 1, 1, and this will be x1, x2, x3, and this will be x1 square, x2 square, x3 square. So I factored these 2 out because I know that if I take a constant multiplied by a row, the new determinant, the determinant of the new matrix will be the old determinant times 2. Now, so what I want to do, I want to look at this. This is what I want to achieve. I can see I have x3 minus x2. I can also see that I have x2 minus x1. So what I want to do here, I want to take column 3 minus column 2 to get the current column 3. I also want to take column 2 minus column 1 to get the current column 2. So what this gives me that 2 is still outside there. So column 1 remains where it is. Column 2 minus column 1 would give me 0 in this position. Would give me x2 minus x1 in this position. That will give me x2 square minus x1 square. What about column 3 minus column 2? Will give me 0 in this position. Will give me x3 minus x2, and will give me x3 square minus x2 square. I can now find the determinant along this row. So it's this one times the determinant of the matrix that is formed when you delete the row of 1 and the column of 1. So what is that matrix? That will be 2 times this one. So when I delete the row of 1 and the column of 1, what I get here is x2 minus x1, and here I get x3 minus x2, and here I have x2 square minus x1 square, and here I have x3 square minus x2 square. So let me create some space for continuation. So I don't require this. I already have it. Now, so we can factor out something. Now that we know how to factor out, along this column, you see this one is x2 minus x1 multiplied by x2 plus x1, and this one is, if you factor out difference of squares, this is x3 minus x2 multiplied by x3 plus x2. That means along this column, x2 minus x1 is common. Let me just factor it out. x2 minus x1, or let me just write so that somebody may not see what I'm doing. Let me just go slow, that people see what I'm seeing, what I'm doing here. What I'm saying is that the first row remains it is x2 minus x1, and this is x3 minus x2, but this one can be factored to mean x2 minus x1 multiplied by x2 plus x1. And this one can also be factored. It is x3 minus x2 multiplied by x3 plus x2. Those are the difference of squares. So it's at this point that I wanted to factorize. And I noted that x2 minus x1 is common in this column. So let me just put it outside. x2 minus x1. And this other column, x3 minus x2, is common. Let me put it out. So what is left here? x2 minus x1 go here 1 times, and it will go here x2 plus x1. And then x3 minus x2 will go here 1 times, and it will go here x3 plus x2. So I can now find this determinant, this determinant of this matrix. So what I have is 2 into x2 minus x1, x3 minus x2. What about this other one? This other one will be this minus that, which is x3 plus x2 minus x2 minus x1. So in this one, when you do that, let me just now remove this because we've already used it. When this is done, what we get is 2 into x2 minus x1 multiplied by x3 minus x2. And you notice that here that x2 minus x2 will give us 0, so what we are left there is x3 minus x1. And this is what we wanted to show. If you do some little arrangement, when you do some little arrangement here, you would have 2. It doesn't matter which one begins. So if I were to rearrange, I would have x3 minus x2, I would have x3 minus x1, and I would have x2 minus x1, as required. So just some little arrangement. Now I want to look at the last concept in our discussion today, and I'll begin with a theorem that I not state because its proof exists. The theorem is that let A and B be square matrices, of equal size. Square matrices of equal sizes. Then the determinant of A times B is the same as the determinant of A times the determinant of B. That is very important. And B, that the determinant of A transpose is the same as the determinant of A. And then C, that the determinant of the inverse of A will be the same as 1 over the determinant of A. This one, of course, we know. We've been using it. Therefore, to get the determinant of the determinant of the inverse of A is the same as. I'm not going to examples. You can take a matrix A and B and see if this is true. For example, if you are to take A to be 2, 1, 0, 1 and take B to be 4, 1, 1, 0, then there's 0. So can you prove that, can you show, using this, can you show that the determinant of A times B is the same as the determinant of A times the determinant of B? So you first of all multiply A and B there, and then get the determinant of the resulting matrix, and see whether it's the same as det A times det B, because you can find det A here to be 2, and det B here you can find it to be negative 1. So that A times that B will be 2 times negative 1. And then find the transpose of A and see whether the determinant of that transpose is the same as the determinant of A. Then also find the inverse of A and then the determinant of that inverse and see whether the result will be the same as 1 over det A. Now I just want to use an example. I want to look at an example that will apply this theorem. Example is let the determinant of A be 3 and determinant of B be 7. Find the determinant of B square multiplied by S cubed multiplied by A transpose multiplied by the inverse of B multiplied by the inverse of A. So the question is, find this determinant. So the solution, the first part of the first theorem of the previous theorem says that the determinant of B square times A cubed times A transpose times the inverse of B times the inverse of A will be the same as the determinant of B square times the determinant of A cubed times the determinant of A transpose times the determinant of B inverse times the determinant of A inverse. And B square is just B times B. So determinant this, if you use the second bit, not the first bit, this is same as the determinant of B times B, which is of course determinant of B times the determinant of B. or determinant of B square. So that is what I mean, that this will be determinant of B square. And using the same reasoning, this other one is the determinant of A cubed. What about this one? We said that the determinant of A is the same as the determinant of the transpose of A is the same as the determinant of A. What about this? The determinant of the inverse of B is the same as 1 over determinant of B. And this one is same as 1 over determinant of A. So when you use the above theorem. But what is determinant of B is 7. So you're talking of 7 square. And this one is determinant of A is 3. So it's 3 cubed there. And determinant of A is 3. And 1 over determinant of B, which is 7. 1 over determinant of A, which is 3. And when you do this using a calculator, you would get 189. You would get 189. That's the determinant of this. So I've just used that theorem. Then lastly, let's look at orthogonal matrices. I'll define what these ones are. A matrix is said to be orthogonal, but let me say a square matrix. It must be a square matrix. Just a minute, let me say. I'm looking at the definition. A square matrix is said to be orthogonal if the transpose of A, so a square matrix A, let me call that square matrix A, is said to be orthogonal if the transpose of A is the same as the inverse of A, or if A times the transpose of A gives you the identity matrix. So any of this, of course this one means this. Of course I know that A inverse times A gives me the identity. So if the transpose of A is the same as the inverse of A, then it means A times the transpose of A will also give me the identity element, the identity matrix. So this is the definition of an orthogonal matrix. Let's look at an example, and that is our last example for today. So the example says, show that A, which is cos of theta negative sine theta cos theta is orthogonal. Show that it's orthogonal. Solution: I only need to show that we need to show that A times A transpose gives us identity. So what is A transpose? The transpose of A is, we make the first column to be the first row be the first column, and the second row we make it to be the second column. So what is A times A transpose? It will be cos theta negative sine theta cos theta multiplied by this transpose, which is cos theta sine theta negative sine theta cos theta. So when you do this, cos theta times cos theta will be cos theta square. And this time this will be plus sine square theta. So it's this row and this column. I get cos square theta plus sine square theta. Now what about this row and this other column? I would have cos theta sine theta minus cos theta sine theta. I'm done with this row and this column. What about this row and this column? I would have cos theta sine theta, and this and that I would have minus cos theta sine theta. This row and this column I would have sine square theta plus cos square theta. Creating this space here, I can do the last part of this proof. If I create some space here, I know that cos square theta plus sine square theta will give me 1. I also know that the cos square theta, no, cos theta sine theta minus this will give me 0. I also know that this will give me 0, this part. And this other part will give me 1. And this is the identity. So we've proved as required. We proved that hence the matrix, hence A is orthogonal. Because we've shown that A times the transpose of A gives us the identity matrix. And that is what we needed to show. The other way you would have wanted to show is you would have wanted to find the transpose of A and also find the inverse of A and see whether the two are equal. If the two are equal, again, you conclude and say that A is orthogonal. And that is the end of our lesson today. If you've not subscribed, remember to subscribe so that whenever I load other lessons, you can easily find them. Thank you for watching.